Thank you very much. Good afternoon, everybody. First day of PyConDE 2019. And probably the second tutorial of the day. And here's the time slots. My name is Mike Müller, and I will be the presenter of this tutorial. I would like to introduce myself a little bit, a few words. So I've been a Python user since 1999. I started with version 1.5, and I lived through all these Python versions up to recently. And I started doing Python training in 2004, and that's actually what I spent most of my time on. I teach Python and I organize Python courses, and therefore also I'm teaching this tutorial. So maybe a few questions about your background. Please raise your hand so that I have a basic understanding how much Python experience you have. So who programs with Python less than 1 year? Please raise your hand. Very few people. Between 1 and 2 years, also a few. Between 2 and 5. Okay, that seems like majority. More than 5 years, also a few people. So we have a good mix of people. But this tutorial is designed to give you an understanding of decorators. You need to understand how Python functions work and basic Python knowledge, more or less intermediate Python. And we want to dive into decorators. And you should be able to understand if you know how a function works. And if you know that everything in Python is an object, you should be all set. We don't need to know much about object-oriented programming in Python, though that's not the real topic of this course. Please download the zip file. I will upload this again. In there you find a PDF with a documentation. I have it here just to follow along. And I will work in a Jupyter notebook. If you know what it is, you're welcome to use one, but you don't have to. You can use any tool you prefer. So you're totally free to use a tool. It's not about the tool here. It's about decorators. And I would like to show you how to write your own decorator. User decorators, obviously, it's very simple. So we will see something how this works. So that's the download URL. So I would recommend to you to have a new directory. That's what I did. I created a new directory, and I'm working with environments. I have an environment here, and I use Jupyter Lab here to work with. If you know how Jupyter works, you're welcome to use Jupyter. If you don't know, I have to say something about the port. Somehow my setup is mixed up, so I have to come up with a port number, otherwise it's not going to work. So Jupyter Lab is just a tool that helps you to work with Python. And since we are the PyData here included, probably a lot of you will know how this works. And I will make a new that's not going to really work. I have to do this one. New notebook. So a Python 3 notebook, and I would like to rename it first and call it Decorators. So I'm pretty much following. If you download, you will also find the PDF. I'm pretty much following the PDF, and I don't want to be too fast. That's why I pretty much retype everything here. So when you download something, you should see that's a notebook. You should see the PDF, and that should be a directory, decorators, which is a few example scripts I gave you, because a big part of the training of this tutorial will be about examples. So what you can do with decorators on top of how to write your own decorator. So first I would like to give you a motivation. Why do we need decorators? So actually the principle how a decorator works is be much older than the decorator syntax. The decorator syntax is this add sign you might see. So this is rather new compared to the principle. And I show you an example why a decorator can be useful. So let's assume you have a class C. So in the documentation, you still inherit from object, which you have to do when you work with Python, hopefully Python 2. Hopefully nobody of you has to work with Python 2. So if you work with Python 2, you need inherit from object. In Python 3, you don't have to do this anymore. And you would like to have what's called a static method. So static methods in Python are actually not needed. You can always write a standalone function, but sometimes you want to have like a standalone function still be inside the class. And this would be just a normal function here, which does something very useful. And you see, there's no self. When you write a normal method, you need to put a self. And to make this one a static method, you have to do something like this. That's the way you did it before you had the syntax. Now you can make an instance of this class. And now you can call this function on the instance, and you can call this one on the class with the same syntax. This wouldn't work with a normal class with a self. And it only works because you put static method there. So obviously it's very important to know that func is a static method, not a normal method. But you hide this very important fact at the end, because you need to have this function object here defined to be able to actually use it. And imagine if this method is a little longer, not only one line, but a few lines, then this might be go out of the screen. You don't see this important fact, and you think the person forgot the self. Yeah. So, and this was one of the motivations why we have this add decorator. So you can achieve the same thing. I just copy the cell. So I can get rid of this whole line here. I don't need this line anymore. And now the decorator, this one is now exactly the same. So the cell, I copy the cell again. There's two cells. Both cells I see here do exactly the same. And that's the main gist of what the decorator is doing. So the decorator takes your function and returns a modified version of your function, or method in this case. So function and method are technically exactly the same, only that methods live inside the class. So if you say function or method, it should be the same thing. And this is what the decorator is doing. So this decorator syntax with the add sign is doing exactly the same. And you can see I can use the same static method. The static method is exactly the same thing. Only it turns in a different color because Jupyter Lab recognizes it as a special syntax as a decorator. But static method is just a function that takes a function and returns a new function, new version of the function with the same name. So if you understand this one, you know already how a decorator works. And you can always use a decorator this way or this way. Most of the time you use the add sign, but sometimes you also use this one, because the add sign, you have to actually literally type the add sign in your code. Here, since you have a function, you could use different method, because static method is a function and the function is an object. You can put this static method into a list or a dictionary or anything else and use it programmatically if you like. That would be sometimes useful. Good. This is the motivation for writing a decorator, but now we want to write our own decorator. How to do this? And we're going to look at how to write your own decorator. We do it naively first. So I write a function that's called hello, that takes a function and prints hello. So you do something like this. And now I have another function. I'd say I use hello as a decorator, and I define a very complicated function that adds x plus y, x and y. Return x plus y. So we will redefine this function multiple times. So it's not about the function, but it's about the decorator. And as you can see here, the minute I define this function, the decorator is executed. So a decorator is executed at, some people say compile time or say import time. So if you put this in a script and you import a script, if this is on the left side of the script, it will be executed immediately. Of course, what happens? So this is equivalent to what? So if you go with this one, so you say add equals hello add. That's what happens. So both cells are equivalent, and this hello will be printed out the minute I define this function. There are some disadvantage of this approach, what I do here. Of course, if I try to call my function, it doesn't work, and it gives me this very common error message, non-type object is not callable, because what did I do? The hello doesn't return anything, and if I don't write return, it essentially puts return none there. So this decorator, while I can apply it, doesn't do anything useful. So you can write a decorator like this, but it's typically not what you want. You have to improve your decorator. So let's write a decorator that looks more like something that you would use. So for this one, we have to make it a bit more complicated. So I use hello, and I get my function. And most of the time in a decorator, or the most common case, is you define a new function inside a function. So in Python, there's no limit how deep you nest this. So you can write a function inside a function inside a function inside a function. As long as you understand what you're doing, there's no problem with it. And then you have this internal function. The name of this function doesn't matter. You can call it whatever you like. There are different approaches. We will see some of these naming approaches. I have this one, and then I use args and keyword args. Who does not know what the star and double star means? Please raise your hand if you don't know what it means. A few people? So let's explore this very quickly. So if you write a general function that has an args argument, and I just print it, yeah. Now I can call this function without an argument, and I do get an empty tuple. I can call this function with one argument, and I get a tuple with one element. You see this comma is necessary for a one element tuple, because just the normal parentheses just means grouping, and the one would be group this itself. So you would need this comma there, and you can call it with two arguments, and you get the tuple with 2, and with 3, with 4, with 5, with 6. So this is star. The star is kind of harvesting all the arguments you supply, or positional arguments you supply. If you don't supply any, then there will be an empty tuple, otherwise they will be put in the tuple. So I can now extend this one and use a double star. So the name KWArgs is not required, but it's a pretty strong convention, I would say. People do this all the time. And now I have a different function, and this function, if I call it, gives me back an empty dictionary. And if it call it with one keyword argument, it gives me back a dictionary with one element, or one item, I would say. And if I put this 2, call it this 2, I get 2 back. So you can combine this, and this is what you can do here. So I say keyword args, and I just print both of them. Yeah, and if I call the function without anything, I do get back an empty tuple and an empty dictionary. And if I call this with positional arguments and keyword arguments, something like this, then I get back a tuple and this one. So I can write a very, very generic function. That's what we want here, because you see, our decorator will take a function and will return a function, as we'll see in a minute. And this should be very generic, because we don't care actually about the original function, how it looks like, what the signatures, what kind of arguments it takes. We don't care. We want to write it for any kind of these functions, and that's very needed. So this is one way of using this star and double star, and the other one is when you actually call a function. When you call a function, it does exactly the opposite. So print. If I print something here, and I don't have an A, better to have something to print. So I print something, and it prints it. But if you look at print, yeah, this gives me the help, then you see print takes optional arguments, and these can be keyword arguments. Or value, it takes value, 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 and I can put in multiple arguments. So I can say print 1, 2, 3. That would work. If I have a tuple with 1, 2, 3, I can print my tuple, which prints the tuple as is represented. But now I can use my star again, and here it takes the tuple and unpacks the tuple, and this would be equivalent to writing print T0 T0. So I tend to change keyboards. Sometimes on the PC keyboard, so it's a bit different. So this would be the same thing. That's actually what it's doing. So it is not very convenient to write this one. But you see that what happens. So instead of writing something like this, I can use a star and unpack it. And the same happens for the double star and unpacks it and would use a dictionary for this. Okay. Once we know all this, how this works, now we do have the opportunity to redefine our hello. So we write this wrapper function, and this wrapper function is adding functionality. So with a decorator, you can add functionality to a function. You cannot really take away functionality because the function called this original function is kind of atomic from this perspective, and you cannot take any functionality away. But you can add something, and you can say print hello here. And then I can return what the original function actually produced. This is very common. You don't have to do something like this. Sometimes you have use cases where you don't do this, but in most cases you want this. And now we do something you might have seen before. We return the function. So the function hello produces a new function on the fly. So now I'm so far away from this one. I just copy the cell down here just so you can see it. So, and now we can use our function hello and decorate our function add, which I need to redefine if you do it this way here. XY. Yeah. And we return X plus Y. So now nothing happens at definition time, at import time if you want. So there's no print of hello, but now when I say add, I do get my result, 3 and 4 makes 7, and at the same time I have additional functionality, in this case it prints hello. Why it's like this? If you look at add, then you see actually add is not add anymore, but is this our wrapped function. So this function has been produced the minute I defined add, the add hello, the add sign hello, call this one and produce this function. Again, this cell is equivalent to saying add, if I define add without the decorator. So I promised to you that we re-implement this function multiple times. And I say add equals hello add. That's what happens. So this is very important that you understand this one. That's what happens. And you see hello returns a new function which replaces the original function. So you have this name here, add. Actually, normally when you define a function, the function name is the same as the string you used here, but here now name is different because you didn't do it properly yet, and now the name is wrapped, and as you can see here, that's a wrapped that lives inside the other function. It has something with a closure and so, but it doesn't really matter now. It's a function that has been produced at runtime. So in Python, everything is an object, including functions. That's why there's no problem whatsoever to return a new function from a function. And that's the main concept of decorators. And that's producing a function from inside in a function worked before the syntax with the add, but you had to do something like this. Yeah. So you could modify a function at runtime with this method, but the new one is using this add decorator. Okay, that's pretty much what you need to know about decorators. Any questions so far? Okay, now the rest, everything else we cover now, it will be details, but some details can be interesting. And also we're going to cover a few best practices, actually how to do it in practice, and I will show you some examples. Good. So, there's two things. One of them is the name is not really nice here, so the name you're using is not very nice. We will fix this later on. And also I hardwired the hello. So if I would write a goodbye decorator, I would need to implement pretty much the same thing. The only thing I need to change is a string. So the functionality is nearly the same. There's only one small difference. Whenever you have this case that you do nearly the same and there's a small difference, hopefully you can parameterize it. So use this string as a parameter to make this more generic. And you can do this in Python by adding yet another layer. So here I add another layer of functions here, and I make it more general. So I say now this is a function say, and I say a text. And now I take exactly this, and now I need to just change it. Now there are different ways of doing this. Very often, the user underscore. So there's one way of naming these things, because these internal names, you don't want to see them again. They're just helper names. So you have this strange underscore name here on this wrapped, I call to underscore. See, this is one pattern to do this. And now you see here, I don't print hello. Text or the greeting, if you like, but text is more general. And of course, now I cannot return wrapped here, but I return say, and I do another return underscore say. So this is a common pattern if you want to parameterize your decorator. It looks a bit scary, but actually it's pretty easy. So I have 3 defs and 3 returns. So in most cases you want to match it. You can have functions, the inner function could work without a return, but most of the time you want to have the original functionality. That's why you call func in return the value, though therefore you have 3 defs and 3 returns. Very easy. And now I can redefine my function. Say hello. And as you can see, I can re-implement my function. You may minimize with a space, and we return x plus y. And now I can call my function. It still works, and it prints hello. And I didn't hardwire hello inside the decorator, but I can supply it as a parameter from outside. Now we have this 3-level decorator, which allows me to parameterize it with, in this case, a text I print out. And of course, you could redefine this function, that's what I'm doing now, and use a different string. Shouldn't be come to it with a surprise. So with a different string, and then you can say goodbye. And then if I add something with my function, now it says goodbye, not hello. In fact, you can stack decorators. You might have seen it somewhere. So there's no technical limit, as far as I know, how deep you can stack them. And then if I have my add function now, it still works, but now it says hello and goodbye. So now I add 2 different features to my function. It prints 2 different strings, which I can supply as a parameter. So this is pretty common if you do web programming. A lot of those web frameworks offer something like permissions or something with these decorators. Question? Yeah. Yeah. So that is an interesting thing. So let's do this for this one first. So this is exactly the same. So if you take this here and you want to have the same, let's do this with the one first. So now you define the add first and then the say later. Yeah. So you have this one, and then you go with the same procedure. Then you say add equals. This is the first call of say, which does the first return, the outer return. And then this, I call this again, and I give it the function add. Yeah, that's an easy one. Now, if you want to do it with 2, so I have to think myself to put it in the right place. So then here you have 2. You call it say with hello first, and then you call it with goodbye. So you do it twice, and that's not that easy. See if I get it right. I call say on this one. So say returns something with goodbye. And of course, then you need to put parentheses in here. Hopefully this is correct. Yeah, so it gets a bit hairy here. And it says goodbye twice, because I put goodbye twice in there, which makes sense. So you have to put the hello first in here. And that's what it's doing. Yeah, so a lot of parentheses, yeah. So the decorator one is much easier to read, but that's actually what happens. So if it's difficult to read, you might try to indent it a little bit, because you can always, so something like this, It's up to you if you prefer anything like this, whatever way that looks good to you. I'm not sure if it looks better. It doesn't really any better, so it doesn't really help. But you could try to do something like this. This application is still useful because now I can have two versions. Here I use the same name, but I can use a different name. So if you want to have the original version and the decorated version at the same time, this would be a way to go. We will see if you do it right, we can still have the original version. The original version can still be there if you use what I call best practice. So obviously this is easier to understand than the second version. But that's what happens. So you can parameterize them, you can chain them, so you can put as many decorators as you like. And sometimes you can do this. Good. So when you talk about decorators, most of the time you talk about function decorators. So function decorators have been introduced, I think, 2.4, something like this, quite a while ago. But since 2.6, also not that new, it was also more than 10 years ago, we have what's called class decorators. Class decorators. The good news is class decorators are simpler than function decorators. You can use the same principle for a class. So if you like, you can define a function. You gave the great name Mark here. And I have a class. And the first thing you need to do, you need to return the class, otherwise it's going to work. And this one doesn't do anything, but now I can do something to my class. I can read, but I can also add something. And now I can use my decorator and I can find a class which doesn't do anything, so I put pass here, otherwise I get a syntax error. And now if I make instance of my class, actually I don't have to make instance. I can do it without the instance. Of course, I add it to my class. Then you see now it has attribute new, which it didn't have before. So very easy. So it's doing the same thing as if I would have my class B. That doesn't do anything. And then I say B, capitalize B, equals mark B. Then B has this new. That's what happens. Exactly the same principle. So mark is just a helper function which takes a class and returns a class, and you're free to do whatever you like. In this case, I add an attribute. Maybe not a good idea in real world, but maybe sometimes you can use it. But you can also inspect the class. So you can go inside the class and can check if the class, what method it has, how long the method names are, and so on. Before class decorators, you would have to use a meta class for this. Meta classes are way more complex than decorators. This is pretty easy to understand. Compare the meta class. Meta class, I need to explain an hour to get to this explanation how a meta class actually works. Meta classes, most of the time you don't need them. Very few people need meta classes. Class decorator is much simpler, and you can apply a class decorator to a meta class. There's one difference when you use inheritance. So once you use a meta class, all child classes inherit will get it. Here, you have to apply the decorator to each class. So inheritance, it doesn't propagate through inheritance. That's a difference. But otherwise, you get the same functionality. So class decorators are actually conceptually simpler because you don't have all this def thing. Yeah, you get a class and you return a new class and you're totally free to do whatever you like, because a class has a lot of properties. So this is also a use case to looking inside the dict. So the dict is a mapping proxy. It's essentially a read-only dictionary, if you want, which behaves mainly like a dictionary. You can look inside and you see all these attributes. In use one we added, and a bunch of this double underscore, leading and trailing double underscore, called dunder attributes. Yeah, the doc string and a bunch of other things that are always included, the module name and so on. Yeah. And then you could inspect it if you have methods, and you could check for whatever things you want. We do an example. We have an exercise with it. So now that's the basics. And now look at the best practice. Best practice. See, practice. I think so. Practice. When we go back, now I go back to the simplest example that works, and which would be our add or our hello without anything. Yeah. So because this has nothing to do with parameterization and this nesting or all those kind of things. So if I do this, I have this one, and I add my hello to my add function. So we did this before, I guess. So, and now if I look at the name is gone. And also if I, which I always should do, I add a doc string. Yeah. So I add a doc string, and then I look at my add. And there's no doc string. I lost my doc string. That's bad. What's the solution? You should always use functools reps. So from functools, so functools is a module of the standard library. You should import reps. So there's nothing to eat, but a helper function that helps you to make a nicer decorator. So if I go to my decorator, then you have to specify here, and ironically enough, it uses a decorator to make a nicer decorator. So you apply the decorator reps, and you tell them to use your function func. Yeah. So now Python knows, okay, this rep is going to wrap the function func. So this is the thing you always should do. And now if I do the same thing again, I define my function. Yes, if I find my function here now, and I look at my add, now it keeps the signature and keeps the doc string. So these attributes are preserved, because reps, if you look at implementation of reps, it's doing not much more than going into the original function and getting the attributes and adds it to the new function. So the new function, it's a different object, but for most practical purposes, it looks like the original one with added functionality. So the name is okay, the doc string is okay, and so on. Yeah. So if I say add.name, then it keeps the name. And there's also I forgot the name, the original, the wrapped. Yeah. So you also have access to the wrapped function. So if you want to call the original wrapped function without the functionality, you still have it. Yeah. Now it still does x plus y, but without this printing of the hello, where the decorated one puts this hello there. So you still have access to the original function just in case you need it. Maybe you want to test something without the decorator, you could test wrapped. These standard names are special internal names. So there are some considerations. If you write tests, you might access them. If you, so some of them can be accessed. So read access is fine. Write access, so these ones you have to be very careful. You have to know what you're doing. Yeah, this depends, but wrapped is explicitly there. And of course, you could say original function equals add function.wrapped, and then you have a better name to the original function, which can be useful. Good. There are a few things you have to consider if you use recursion. So recursion is supported in Python, but it's for many cases not the right tool. So Python 3 now has a recursion limit of 3000. As a function calls itself 3000 times, you get a recursion error. So recursion can be used if your problem is really recursive and you don't have to recurse so deeply. That's fine. But don't replace loops with recursion. That's typically not the way to work in Python. Can make your program very slow. So if you decorate a function, the function calls itself, it calls the decorated version. That's something you have to be aware of if you have recursion. There's just one example here that when you recurse something, you will get the decorated version. Good. That's a theory of decorators. So everything is a function. Python, you can define functions inside the functions, you can return functions, and then the decorators are just a nicer syntax to replace an existing function with a newer function. Plus, we also have class decorators, which do exactly the same, but with classes. Any questions so far? Good. So the rest is use cases. So I would like to show you some use cases, and then they also use some other principles here. So if you downloaded this zip file, then there's a directory decorators with a bunch of these examples, and we go through one by one, and this might give you some inspiration what you can do with these decorators. So the prime usage for decorators is what's called cross-cutting concern. So you want to do something in many places in the application that has nothing to do with your application logic. And I have a few examples here. You see logging is one, caching is one, and argument checking could also be one. And let's have a look at these. So I load my argcheck here. And this is a check function arguments for given type. So Python is dynamically typed. You might know that Python supports type hints, which are just used by tools before you start your programming, and there's no runtime type checking. Sometimes it might be useful to implement something, and a decorator could be one way to do type checkings. Like if you need to talk to the outside world and they need special types, then you can just use any type. Then you can check the type here. That would be maybe one useful example. So we use func tools as always. And here I use this 3def. So if you have 3defs, I have 3 returns, remember? And I use outside, I use check, which is my decorator. And here I use a star syntax. Remember, star syntax means it takes an unspecified number of positional arguments. And these will be the types. So I specify the types I want. Then the next one is a func. And then the internal one is the one that's wrapped with func tools wraps. And this is the body of the whole thing. Yeah? You have to return down here. And here I check two things. First, I check that the number of arguments match the number of types I specify. So arguments is a tuple, has a length, and archetypes is also a tuple, has a length. And if this length doesn't match, I raise an exception and say, okay, type error, and I assemble a message and say, okay, I expected so many, and I got so many. If the first thing is fine, so the length matches, I do the same thing. The next thing I do zip. So I zip together the arguments I actually get and the types I expect. Yeah, this is my argument and this is my type. And if this argument is not an instance of the type, I raise an exception. So when you do type checking, it's highly recommended to use is instance, not type. So type would check for the specific type. Is instance would include the parent class. Yeah, so that would account for potential inheritance. So in most cases, you want to use is instance, and that's why I use is instance. And if it doesn't match, again, now I assemble an error message and I raise type error, and I use here the type I get and the type I expect. Yeah, I just use this one, and I just create an error message with as much context information as I like. So now I executed the cell. Now we have a check, and I can now say check, and I can specify types, and I say now I want to have 2 floats for my add function. And once I do this, still looks the same. And if I try to call my add function with 2 integers, it doesn't like me anymore, because it says now expect the class float, but class int. So if I just add a dot here, which makes it an integer and float, now it works. So I can now, with this decorator, force this function to take only 2 floats and nothing else. Yeah. So this would be the type checking you can supply here. This, I don't recommend use type checking all over the place, but there might be a few cases where this is very useful, especially if you want to save something in a file somewhere or in a binary format and it has to be a special data type. Before you do it, you might be able to check this here. Good. This is the principle. So I write this small helper, yeah, and I supply the types, and then I check the types of the function. Likewise, if I call my function here, the normal function would have called this already. So, but if I call only this one argument, I do get a number of arguments error first before I go to get to the types. Yeah, this is normal if you don't specify a keyword, a default parameter, you will get the same, pretty much very similar message from Python. But even if you have a default one, it would still have 2, which is kind of a little bit contradictory then, I guess. So you need to design this one in a way that makes sense, but it's just as an example what we have here. So argument checking is one example. And now this looks pretty scary, but you will see this will be the same pattern again and again and again. It's just what you do inside, it's a bit different. Therefore, the next I would like to load is caching. So I call it cached because caching, I think it's not a library module. Here I use caching means when you have a function that's deterministic, so produce exactly the same output for the same input, you might be able to cache the result. And there are many different ways of caching it. Here I use pickle to generate some cache, which assumes that the arguments to my function are pickleable. Most of the objects in Python you can pickle, some of them you cannot. You cannot pickle functions, you can pickle functions, you cannot pickle file handles, you cannot pickle lambdas, you cannot pickle sockets or something like this. So there are some exceptions, but let's assume everything is pickleable, and now I use only a 2-layer approach, and I have a very simple cache. You don't have to implement the cache yourself. There's a LRU cache in Python already, but there's an example. And you might even use LRU cache in here to modify the behavior with the decorator. Yeah? LRU cache also works with the decorator, by the way. So what I do, I keep a cache inside this function, which is maybe not a good idea because it's very difficult to access it. You could, but it's not typically the way to do it. And then I have my functool reps here, and I have this one. And this is pretty easy. I just generate a key by using dumps. So I take the arguments and the keyword arguments in the tuple, which assumes they are pickleable, generate a pickle object, which I use as a key in a dictionary, and I just put this key in a dictionary. So if the key is not there yet, I call the function, and caching assumes that the function call is expensive. So for our example, x plus y, the caching probably takes more time than calculating x plus y. So this is an artificial example here to show how it works. In the real world, this function should be something at least a few milliseconds or seconds. So if something it's a bit longer and you want to shortcut it and don't want to produce the same result again and again, then caching can be useful. And I put in a dictionary. If it's there already, I just go to the dictionary and return the result. So this assumes if you have the same combination of arguments, I produce the same result. If the function doesn't fulfill this criteria, this caching doesn't work. Good. So you can make your own very simple cache. And now I can use my cached for my add function. And here I make it a bit nicer. I say print, go down. Yeah, do you see something happens? And I return x plus y. So, and if I call it now, you can see if I call this 4 and 5, it prints adding. If I call it again, this 4 and 5, it doesn't do anything. Yeah? So it just retrieves the pre-calculated 9 from the dictionary because it uses a key. The key calculation is probably more expensive than the adding here, of course, so it doesn't make a lot of sense to do anything like this. If I call this function like this, which is totally possible with a keyword argument, it recalculates it again. Because it's not smart enough to recognize that the y equals 5 is the same as the positional 5 before. This is a different case. But there are not so many combinations, so that's probably easier. Maybe you can figure this out, but it takes maybe so much work than just recalculate the result. Next time it will be there. Yeah. So now my cache is not really there. It should be hopefully in the closure. Yeah. And you can see there's two objects in the closure. The closure is the thing what's preserved, what's used to live in the outer function, and now I still need it in my decorator. And one is the function that I'm wrapping, and the other one is a dictionary, which is in the first cell. So if I have add, which is closure, which is a tuple, yeah, and I access the first argument, it's a dictionary, and then I can say, give me the keys, and then it shows you the keys. Oops. No, it doesn't have the keys. Isn't it a dictionary? What am I doing wrong? It's a dict. And dict doesn't have keys? That's strange. Yeah, it's still a cell. So it's cell 0, and inside the cell there's a. So I'm in the cell, and inside the cell there's a cell. Yeah, cell contents. Sorry, cell contents, which is a dictionary, and you see that's a dictionary now. And of course, it's just the pickle. Yeah, it's a binary format with a special pickle protocol, the standard pickle protocol. And you see the 9 is there twice, but once with two positional arguments and one's a positional and there's a keyword argument. So this is not a very convenient way to access a dictionary, so you would need to put it somewhere else potentially to make it more useful, but that's a principle of caching. So you can write your own cache. This is pretty much one of the simplest cache you can write, but of course you could, instead of pickle it to a dictionary, you can use shelf and persistently pickle it for the next time or anything like this. Yeah? You could also have cases and say a few things you don't want to cache because they don't produce reliable results. You only want to cache certain types of, or the result only for certain types of arguments. So if you need a cache that's a bit more sophisticated, then you can use it. LRU cache in Python does most of it already, and you could actually use it, but you could write something around it to make it more specific to your needs. And this would be a very prime example for Decorator. Good. So another example, the next one is logging. So a very common way to write a decorator would be logging. Logged. So, and here I make it a little bit different. So this from future import is just for Python 2. I probably can take it out pretty soon. Func tools, and I have a constant logging false. It's like a global switch. I can turn something on and off. And this is again a 2-level decorator with 2 defs and 2 returns. Looks exactly the same. We take the function, we have the wrapper with the args and keyword args, and then I'm using logging. So if logging is on, I do something. Otherwise, I just return the result of the function anyway. So if I do this, and I use this locked decorator locked in front of my grade add function. And I call my function. Nothing happens except the production here. But if I have this global, so it's a bit strange. I use a constant, I change the constant. I don't know if it's a good design decision, but I do it anyway right here just for the purpose of showing you. And now if I change this constant at runtime and I call add again, now the logging is on. So instead having if in all these functions that are to be logged or not, I just change one global switch and all the functions that Decorator will do logging. So, of course, in reality, you wouldn't just print log, you would do some logging. So now you could use Python's logging module or some other solution to do some actual logging, and you can globally turn on and off logging. Of course, you could make it more sophisticated, introduce turning on and off for different log levels and so on, if you like. But this would be something you can do with a decorator pretty easily. And in a real world, that will be maybe a bit more complex than this, but this would be the logic. Again, cross-cutting concerns is a main application of a decorator because logging has nothing to do with your business logic, but is something you can use potentially for many different libraries because you want to do logging. Yeah? But actually, what the logging is doing, we can also, you could have another layer and supply the logging function as an argument and then call the logging function. I have another layer, 3 defs, and outside you introduce the logging function. You can inject whatever logging function you like with a decorator. This would also be possible. Good. That's logging, another thing, and here we have this global switch. One more example with functions, and then I do have one example with classes, and then we do have exercises. So, any questions so far? When you have questions, yeah? Yeah, so it's calling of functions in Python is comparatively slow because you always have to look up the name and do things. So depends what you compare it with. Yeah. So if you do a call to a database, then Python decorators are probably much faster. So if you call a function in a loop again and again and often, you might be, if you have a lot of extra calls, you might slow it down. Yeah.
I saw that the decorator is only called once at the import time.
Yeah, the decorator. But if I, but I replace, let's look at this example here. Yeah, I replace the original function with a function. So I call this function and then I call this function. So this is not a good example because it's caching here. Yeah, I return a new function. So this function checked will be called. So you're right. This one is only called, the outermost one is only called at import time. But then I replace the original function with a double function. So for each normal function call, I have 2 function calls because I call the outer function, the wrapper, and this one in turn calls the function here. That's the second call. So I always have a second call. If I have this, most decorators are like this, that I want to change behavior when I call a function. If I don't want to do this and I use the decorator as our very first hello, that didn't work, it would have worked if it just returned the function. So remember the very first one, yeah, this one. So if this one didn't work because I didn't return anything, but if I return the function unchanged, then there wouldn't be any new runtime overhead. But the decorator would be executed only at import time. Sometimes, actually our next example is exactly. Sometimes you want this. More use cases are typically you replace the built-in function. That means you call the wrapper and the wrapper calls the original function because you want to have some functionality of the original function. Unless you want to turn it off totally, that's also possible. For some testing, you want this function, does this be called, but you don't want the function to do anything, then you could turn it off. That would be another application for a decorator. Yeah, but the way we do it here, for most cases, you would double the number of function calls, which adds overhead. Yeah.
For the check decorator, is it possible you can remove one of the wrapper functions by appending
Probably you could. Just a minute. You can add. The question is, you could add attributes to functions. That would be something you could do. So let's look at the check. Argument check. So now we make it a parameterized run with 3 def and 3 returns, and the outermost layer gives you the arguments. You could also somehow get the arguments in a different way. Yeah, and you can add attributes to a function, but only after the function is defined. I don't think you can. The function itself, maybe you can do it in a function. You could say function name dot argument equals something. That's possible, but then you would need to modify the function itself. And if you do it from outside, you would need the function first, and then you can do it. And then you're out of the nice decorator, because the decorator, you can do everything on top, and you see it. That's a syntactic sugar the decorator gives you, and you would lose it. Certainly you can achieve the same functionality with different ones or different methods, and maybe get rid of one of these layers. But the thing is that the decorator is a bit more complex, but you write it only once and then you can forget it, just use it. So you have this complex thing written once, and you don't have to bother in your source code. If you have a different solution, you have to tell the user you have to do 3 steps, then you offload more complexity to the user. Here you put the complexity in the library, the decorator as a library, and then when you use it, it's easy. That's probably the better solution. But certainly there are different ways of doing it, but once you have a decorator anyway, you can as well make it a parameterized decorator, which makes this much easier to understand, because people understand parameterized decorators, and using it, you don't have to understand how it actually works internally. You just use it like this as a recipe, and you don't know what it's actually doing. It's still okay. Of course, it's always better to understand why things work, but you don't have to necessarily. Any more questions? Good. So let's go to our last example for registering. Any kind of a registry, so it's not necessarily the Windows registry here. Registering, and this is a concept you want to do something beginning, and like if you have a framework, who knows the difference between a library and a framework? So typically you import a library and call functions of a library. A framework turns it around. The framework, you write code, and the framework is calling you. That's more or less the definition of a framework, something like this. And if you want to give the framework something to call, you can register it. So if you want the user to extend the functionality with some kind of plugin, this would be a very poor man's way of doing this. There are very good libraries that help you to write plugins, but just for the understanding. I do have a registry, which is again a dictionary, and I want to do something. And I have 2 different register ones. So register at call and register import time, which also has an implication to this overhead. So register, let's look at the registry at call first. It's a 3 level, because I want to have different registries with names, so I can supply a name. And then we have our def, reps, args, keyword args. So the same pattern. So you can take this thing as a scaffold for your own decorator and just replace it with different names and different arguments. And then I use a set default, which I hopefully know this means I go to the dictionary. So if the name is there already, I append to an existing list. If not, I put a new list and append to it immediately. So for this one, I don't have to check if there's something already, append to it. Otherwise, add a new list. Set default is doing this for me. Has nothing to do with the decorator. It's just a normal dictionary method. Yeah. So I do this, and then I just return this from the function. I do my standard return. So let's have a look. So if I look at the registry, which is an empty dictionary, then I use my decorator register at call, and I give it a name, simple, and again, as I promised, redefine our function. So if I do this, and if I look in the registry, what's written in the registry? Anybody? What's in there? Nothing. because I haven't called my function yet. So the name should use the name. If I call my function, I get my result. And if I look at my registry again, then you see now the function ends up in the registry. So now when somebody calls, something happens to it. So then I know this function has been called. If I look at the registry, I know this function has been called. In this case, I just add the function object, but you could also do something else, whatever you would like to do there. Good. This is the first one. The second one is register at def. Looks very different. So there's one level less, even though I have a name. And I do the same thing here, but then I return the function unchanged. And this wouldn't do any overhead because I just have this at import time once. I call this register at def once, and then I return the function unchanged. This is not that common, but it's possible to return the function unchanged because I don't want to change the functionality of the function. I just want to have a side effect when the function is defined, and I know somebody defined a function. So let's do this. Clean our registry. So registry is a dictionary. That's why I can say clear, which clears my registry. Yeah. And now I use my decorator, register at def, and I define my function. And I did a mistake. I have to make it give it some kind of string because I decided to do something like this. And I return what I'm doing, x and y, x plus y. So, and now if I look at my registry changed the minute I defined a function. And when I call my function, nothing happens. You can call the function as often as you like. It doesn't change the registry again. So the registry is still the same. Yeah. So these are two ways to do some kind of whatever you want to call it. Sometimes you want this now. I know my user defined this function and marked it in a special way, and I can find it. The other one is doing something that what the function is called. Now I know this function is because this is kind of a special function, and I can see if the function is called or not. These are two applications of whatever you want to subsume under this concept of a registry. You have some kind of thing that happened, and you have a feeling what happened. Good. One more example for a class decorator. So far, all the decorators are for functions, and very often you will use decorators for function, but you can also use a class decorator. So I define a function is called assert fluid. Yeah, and I give it a class. And when you do this, the first thing you should do, return class, because I tend to forget this one. And now you write the body, whatever you want to do with a class. So I use assert. So assert means make sure that this, what's right on the right-hand side is true. If it's not true, you raise an exception. You have to be careful. It's not exactly the same as doing exception handling, because if you call Python with -c at the command line for -o, for optimized, then asserts will be turned off. So you can turn off asserts at runtime. They're just for something for debugging. But I use it here, but be aware. So if I check that I assume that my class has a attribute temperature, and this temperature is supposed to be in this range. Yeah, you see, it's degrees Celsius, and we assume 0 and 100. So some physicists will say, okay, if you have a different pressure and you have some salt inside, and it is not true. But we assume that these are the temperatures to make water solid and water as a gas. So you have, it's not really water anymore. So if I have a class water here, which I decorate with my decorator. 25 degrees, nice and warm, as in a laboratory, then it works. If I do the same thing, and let's call it not water but ice, and ice has negative temperatures in Celsius, so it's minus 25, and I try to define the class, I cannot define the class. The minute I define a class, so at import time, or byte compilation time if you want, I get this assertion error. And of course I can also raise a string here. Temperature must be between 0 and 100 degrees. So it doesn't fit here anymore on my line because I have so big a resolution here, or zoomed in. But just write something like this, and now if you do this, yeah, then you get this message, yeah, whatever you write on the right hand side. So of course, if you want to make it more sophisticated, you could also raise an exception instead of an assertion. Raise an exception, but do it in a traditional way, then it will also work. And now you can, if you put the decorator in front of a class, you can only define a class that corresponds to your requirements for the class, but you can check it at the definition time. That can be interesting. Yeah.
In what use cases would you recommend using classes to define decorators instead of functions?
Good thing. So you can always use a class with a done-by-call method. That's what you mean. That works like a callable. Because actually, you don't have a function. In Python has a notion of a callable, which can be a function, a method, or a instance of a class that has a standard call. Yeah, and if you're familiar with this one, then you can write, because you wouldn't have this many. You can save one level. Typically, I use this method when I have a function that has a state. So normally functions don't have a state. So maybe an example, just nothing to do with decorators yet, but you could do something like this. You could write a class that's called a function. And this is my prime example for this kind of approach. Yeah. And then you have this call method, and this would be actually the function that you do. So you have the self, and you would have, let's say, x and y. You can make it more general, just hand the function in, but do something like this. So I would say self dot counter plus equals 1, and then return x plus y. So now I can make an instance of the function. That's an instance of a class, but it behaves just like a function. And now I have an attribute, and if I call it with something, it does my add, and if I look at the counter increases. So I call the function. So the function knows how many times it's been called. You can do this in a function. The function can have an attribute, but when you have a function, I would strive for a kind of a pure function. There's no such a thing as a pure guarantee for a pure function in Python, so a function without a side effect. Because incrementing the counter is kind of a side effect, and therefore I like this approach. And of course you can use this approach to write a decorator, because you have a function. So it depends. So, but this assumes that you know how this works, and then you can use it, because in the end it's just callable, and you could use the init to parameterize it, and you would achieve the same thing. It would reduce one level of indentation. No, the overhead would be the same. Yeah, and overall, this is just a call. Yeah, so I don't think there's any difference in performance. I would need a test, but I'm pretty sure there's no difference. The overhead would be still there, because you call the under call, which acts as a wrapper for the other function. So overhead wise, it would be pretty much the same, I think. Yeah. So this is a totally different concept, but if you know this, you can apply it, and instead of a normal function, you can use a callable, which would be exactly the same thing. have any more questions. So, we still have a few minutes, I think. Until when do we have? 1 minute left. Oh, I thought it would be 1/2 hour. No? Okay, then you have to have a homework. So write a decorator, and here the decorator, the task is, I just show you, it's a time measurement, and one way would be just the last thing, import timeIt is a module of timeIt, and timeIt gives you what's called a default timer. It gives you a timestamp. Yeah. So and what you can do, you can make a timestamp before, and then you later on after your function call, you do a timeIt default timer again, and say minus start, which tells me that it took me 11.6 seconds to do all this. So this one you can incorporate in the decorator, and this decorator can measure how long it takes to call a function. For instance, cross-cutting concern time measurement. So our cross-cutting concern now is break. So thank you very much for your attention. Hope you learned something.